Hi, thanks for joining me. Today we're going to be exploring L'Hopital's rule and we're going to ask the question, what happens if we do the opposite of what L'Hopital's rule tells us to do? So before I get into what I mean by that, let's quickly go over L'Hopital's rule. Suppose we have two functions f and g, and we're going to suppose these functions are sufficiently nice for this video. We're not going to go too much into the details of sort of continuity and differentiability and things like that. So we're just going to assume f and g are sufficiently nice, and we have some real number a, and we're taking x to approach a, and we're looking at the ratio of f of x over g of x, and we want to compute this limit here. And we're also going to suppose that as x approaches a, f of x goes to 0, and similarly as x approaches a, g of x goes to 0 as well. So we kind of got a 0 over 0 limit, and L'Hopital's rule tells us that this limit here is equal to the limit as x approaches a of f prime of x over g prime of x, provided this right hand side limit here exists. So if we want to compute this limit here, and we've got a 0 over 0 situation, and we know that the right hand side, the limit as x approaches a of f prime of x over g prime of x, if we can somehow compute that, then that will allow us to evaluate this limit here. So that's L'Hopital's rule. And now this essentially says that this guy over this guy tends to the same thing as the derivative over the derivative. But instead of now looking at the derivative, today we want to ask the question, can we look at the integral instead? So in other words, does the limit as x approaches a of f of x over g of x, does that equal the limit as x approaches a of the integral of f of x dx divided by the integral of g of x dx, or something like that? So that's what we're going to be exploring in today's video, and without much further ado, let's get stuck in. Okay, so what we're going to do is we're going to start off with kind of our right hand side, so kind of the limit as x goes to a of the integral of f of x dx divided by the integral of g of x dx. But hopefully if you just stare at this for a couple of seconds, you realise it doesn't really make sense because we've got two indefinite integrals. So in theory, that's going to be some function of x plus an arbitrary constant c, and we can't really take the limit as x approaches a of an arbitrary constant. So to get around that, what we're going to do is turn these guys here into definite integrals. So we're going to do this one from some real number, say x naught, up to x. But then of course we've got to write this as f of t dt. And similarly on the denominator, but now we're going to use x1 to x of g of t dt. Now this does make a bit of sense, at least in theory. But now what we want to do is somehow compute this limit here, or show that it's equal to the limit as x approaches a of f of x over g of x. And now remember, we're free to choose what x1 and x0 are. So what we're going to do is use L'Hopital's rule, in fact, to help us. And if we set x1 and x0 both equal to a, like so, what we notice is that on the top here, if we plug in x equals a, we've got the integral from a to a of a function, and no matter what that function is, this guy here is always going to be 0. Similarly, on the denominator, as when we plug in x equals a, we're going to get the integral from a to a of g of t dt, but that of course is 0 as well. So we have a 0 over 0 situation as x approaches a, so in fact we can apply L'Hopital's rule and note that this limit exists. This limit here is the same as, by L'Hopital's rule, the derivative of the top divided by the derivative of the bottom, and of course just using the fundamental theorem of calculus, that is just f of x over g of x, and if we take the limit as x approaches a, and remember another thing of L'Hopital's rule was that provided this limit exists. So all in all, if we know that this limit exists, we might not know what it is, and that's what we're trying to compute. The limit as x approaches a of f of x over g of x. Suppose we know the limit exists, but we don't know what the limit is. Well, we can actually just work back and then evaluate this into this kind of thing here. So the integral from a to x of f of t dt divided by the integral from a to x of g of t dt, and just essentially going from this side to this side proves why it's valid, and the key step is going from here to here is just L'Hopital's rule, like so. So in fact, the answer to our problem, perhaps surprisingly, is yes, we can kind of do the opposite of L'Hopital's rule and integrate up to get two limits, looking at the ratio of one by the other. But surely if this is so easily proved and so kind of easy to see why it's true, why don't we use it more often? Well, let me clean up the whiteboard and I'll kind of give you a sketch proof as to why. Okay, so before we get into why this integral L'Hopital's rule is a little bit redundant, let's look at normal L'Hopital's rule and look at an example to see exactly what it's doing and why we use it. Well, if we just look at this example here, the limit as x goes to 0 of e to the x minus 1 divided by sine of x. Well, the numerator is, as x goes to 0, is e to the 0 minus 1, so 1 minus 1, which is 0, and the denominator is sine of 0, which is 0, so we've got a 0 over 0 situation, so we can use L'Hopital's rule. So when we differentiate the top, we just get e to the x. And when we differentiate the bottom, we get cosine of x. And of course, don't forget the limit as x goes to 0, like so. And this thing here, we can evaluate because e to the 0 is just 1. And cosine of 0 is just 1. So it's 1 over 1, which is 1. But the key thing here, or the reason why we kind of use L'Hopital's rule, or how it helped, is we turned a 0 over 0 limit into a kind of 1 over 1 limit in this case, but essentially a limit that isn't 0 over 0. Because 0 over 0 is a very ugly kind of looking limit, it's an indeterminate form, but if we can transform it into something which is determinable, in this case 1 over 1, which is exactly what L'Hopital's rule allows us to do, it makes life a lot easier, and that's kind of why we use L'Hopital's rule. The reason the integral case doesn't really work is because if we have it, it does work, but it's kind of redundant, is because if we start off with a 0 over 0 case, when we integrate up, we're still going to be left with a 0 over 0 case. And to see that, let me just kind of give an example using polynomials. So suppose f and g were polynomials. So we have f of x equaling, and we're going to have our a from before, so the thing that we're like x tend to, we're just going to assume that a is 0 for this. And so if f of x tends to 0 as x approaches a, so in other words, if f of x approaches 0 as x approaches 0, and f of x is a polynomial, then that means it has no constant term. So it starts off with its linear term a1x plus a2x squared plus so on, all the way up to say an x to the n. And then g of x, we'll suppose is b1x plus b2x squared and so on, all the way up to now bm x to the m, say. So something like this, and we're looking at the ratio of f of x over g of x. Well, when we integrate f of x, so if we compute this guy here, so the integral from 0 to x of f of t dt, well, this is just going to be the integral of this guy here, but because sort of our lower limit is 0, this is just going to be some polynomial which we can factor out an x from. So it's going to be x times p of x for some polynomial p of x. Because obviously if you just integrate this up, this is going to give you a half a1x squared plus a third a2x cubed, and so on. And of course you can clearly factor out an x from this. So you're still going to be left with an x on the top. And similarly, when you do the integral from a to x of g of t dt, this guy here is going to be equal to x, now say times q of x, where q is some polynomial in x. So you're still going to be left with a 0 over 0 limit, and then that just kind of makes things, you're never going to escape that 0 over 0 limit. So sort of continuing this argument by induction, even if you were to integrate it a bunch of times, you're still going to be left with a 0 over 0 limit, and that's why L'Hopital's rule with this integral trick doesn't really work. Whereas when you differentiate, you can maybe, sometimes get rid of those things that are the same. And I guess to kind of see why, if we can just assume everything is its Taylor series for one moment, then when we differentiate, we're kind of getting rid of potentially one factor. So for example, if we're differentiating, or if we have, say, x squared over x, suppose we're trying to compute this limit here as x goes to 0, it's a pretty dull limit, but if we try to work out what x is, if you try and work out what this limit is as x approaches 0, of course it's a 0 over 0 limit, but when we differentiate, we're kind of getting rid of one of the zeros in the bottom, so now that becomes a 1 and this becomes a 2x, of course. So now this is in a determinable form, whereas of course when we integrate up, we're kind of just introducing more of these zeros, which does not help. If we got something that's 0 over 0, if we multiply top and bottom by 0, we're still going to have 0 over 0, so that doesn't really put us in a situation where we can evaluate the limit. Whereas when we use normal L'Hopital's rule, we differentiate, we can sometimes escape this 0 over 0. I hope that has all made sense, and I hope you've sort of perhaps thought about, maybe you have thought about this L'Hopital's rule thing before, seeing if you can do the opposite, and hopefully just now I've explained why it doesn't really help. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.